Welcome to Quantum Curious, and in today's video, I'm going to discuss squeezed coherent states. So in the previous video, we discussed what are squeezed states and how can we generate it using some physical operations. So we discussed this. We discussed two operations that are uh, parametric down conversion and some interaction with nonlinear crystal. So we can generate squeeze state by the interaction of a strong coherent state with a non-linear crystal or solid. So that's how we can generate squeeze states in uh, laboratories, and they are highly non-classical states. So as we know that the reduction of fluctuations or field fluctuations is related to photon processes, and these processes uh, can generate a squeeze state, and we can represent these operations using a unitary operator. And this unitary operator is usually called a squeezing operator. So we can generate a vacuum squeeze state or squeezed coherent state. So in order to generate squeezed coherent state, we have to use squeezing operator and displacement operator. So we have discussed that we can generate coherent state using displacement operator. So now we can uh, we can use both the operators in any order to generate squeezed coherent state. But the two definitions of the usage of these operator is different. Although they um, generate the squeeze state, but the properties of the generated squeeze state will be different, like in the respect of anti-bunching. So there are two definitions of generating squeeze state. Either we can apply a displacement operator in order to generate a coherent state first, or we have to apply a squeezing operator in order to generate a squeeze vacuum state. Then we have to apply a displacement operator. So we can apply these operators in any order, but the property of or the properties of the generated state will be different in many respects. So we know that the two operators do not commute with each other. So we can write it in another form, like uh, first applying this displacement operator, then squeezed operator, and we can write it in that form by using the unitary property of the squeezed operator. So this beta is some different from the alpha, and it is related with alpha with this relation, and uh, this relation will be very helpful in the later discussion. So if there is no displacement, then we end up with the squeezed vacuum state. So if there is no displacement, we know that we have vacuum state, and if we apply the squeezing operator on it, it is going to end up with a squeezed vacuum state. So squeezed vacuum state is an eigenstate of annihilation operator B with uh, zero eigenvalues. And this B, this annihilation operator B can be obtained by Bogly-Bob transformation on the annihilation operator, and uh, we can also get a accretion operator using Bogly-Bob transformation on accretion operator A. So the squeezed vacuum state is the eigenstate of these two operators. So we will see that how that will be useful in generating the state, that is the squeeze state. So here is a phase diagram of squeezed vacuum and squeezed coherent state. So you can see the difference between the two um, diagrams, although they have the uh, ellipse shape, they are ellipse shaped, but the position of the state is different in phase space. For the squeezed vacuum state, it is ellipsed as it has less uncertainty in even quadrature at the expense of increased uncertainty in E2 quadrature. So it is present at the origin of the phase space. So it is a vacuum squeeze state. On the other hand, for squeezed coherent state, it is displaced by a displacement alpha, and it is also uh, have less uncertainty in even quadrature at the expense of increased uncertainty in E2 quadrature. So this is the difference between these two states, although they are both squeeze state, but uh, they have different properties because they have different positions in the phase space. So our task is to write the squeezed vacuum state in terms of Fock states or number state. So we know that we can write squeezed vacuum state as the superposition of Fock states. And we invoke the property of the eigenstate of the squeezed vacuum state as the eigenstate of the annihilation operator with eigenvalue 0. So uh, putting the annihilation operator in terms of A and A dagger as we shown earlier, and we end up with this relation. So so we have to write it uh, in terms of the Fock state with n number of photons. So we have to change the indices of each sum, and we end up with this expression by using the orthogonality relation of the Fock states. So we want to derive a similar recurrence relation similar to the Hermite polynomials. So in order to get this, we have to make the changes. So we substitute mu in place of cos hyperbolic r, and uh, nu in place of aorta, aorta I theta or e aorta theta sine hyperbolic r. And we have to use the expansion coefficient as this. So after substitution, we end up with these terms as they are here, uh, implying each term and substituting these values that we have assumed in order to get the correct recurrence relation. We end up with this correct recurrence relation. So this is the recurrence relation for Hermite polynomials, where z is this. So we know that it is for Hermite polynomial. So we will assume that an is equal to the Hermite polynomial of 0 order. So we end up with this expansion coefficient. So we have to find the A naught, that is the normalization constant. So we will put the coefficient, that is the expansion coefficient, in this expression, and we end up with this value, and uh, thus squeezed vacuum state in terms of the number state. So in order to get the A naught, that is the normalization constant, we have to use the normalization condition. And we can write it as this, and we can write rearrange and write it in simple form as we have here. The infinite sum, we have to evaluate this infinite sum, and to evaluate this, we have to use this property of Hermite polynomials. So making substitution, and we end up with this expression. So our normalization constant is this. So writing back it into this expression, we end up with the correct expression of the uh, squeezed vacuum state in as a superposition of the Fock states. So we know that uh, the zero order uh, the zero order uh, uh, odd Hermite polynomials vanishes, and the even Hermite polynomials of zero order survive. So we make substitution in it, and we end up with this expression. So we can see that the squeezed vacuum state is the squeezed vacuum state is the superposition of even Fock states. So we can correspond it with the earlier discussion we have that uh, we have to use the two photons in order to get the squeezed state. Uh, so we can correspond it and you could see the direct implication of this proposition here because indeed the squeezed vacuum state is the uh, superposition of the even coherent states. So this is the correct expression that we were trying to derive, and we can also write squeezed coherent states in terms of, or squeezed vacuum states in terms of coherent states by using the uh, identity property of the coherent state at as it is the over 1 by an integral of the outer product of the coherent state like cat and bra and taking integral over the whole phase space. So invoking this expression into mm, using into uh, this write uh, we can write the squeezed vacuum state in terms of current state. So it is depending upon the displacement. And here it is depending upon the photon number or even photon number. So this is for today. So we saw that what are squeeze states and how can we write the mathematical unitary operator corresponding to the physical operation in order to generate the squeeze state. And we saw that how it has implication when we write the when we write the squeezed vacuum state in terms of the number operator or number state. And we saw that it is the superposition of the even number of Fock states. And then we also write the squeezed vacuum state in terms of the current state, and it is directly depending upon the displacement in phase space. So that is for today. If you like that video, kindly share and subscribe.